information about the data, about the test data set. In terms of metrics, we use two metrics. One is a metric called ERR, which is a metric invented by my colleague Olivier. And another metric is normalized DCG. The basic idea of normalized DCG, called NDCG, is trying to normalize the DCG value between 0 and 1. And finally, the result, and officially we use ERR as an official metrics, but that is just for competition. But in many research papers, people still would like to use NDCG as evaluation metrics. And finally, each team only select one submission called primary submission. And yeah, we provide 30,000 cash prize for this competition. So there are two tasks, right? So each task is 15,000. The first position is $8,000. The second position is $4,000. The fourth position is $1,000. So this competition is very active in the year of 2010, and it attracts more than 1,000 different teams to register, including all companies, including Google, Baidu, Microsoft, Yandex, Yahoo as an organizer, we cannot participate. Finally, Google and Baidu, they do not really submit their result, but they registered and get the data. And we have more than 1,000 different users, because some of the team have one user, some of the team have many users. The largest team have 7 members. And finally, we have more than 300 active teams, which means they submit at least more than 2 tasks. For task 1, which is the fundamental learning to rank problems, we have more than 300 active teams. And for task 2, learning to rank problem, we have around 90 different teams. And in task 1, overall, we have more than 3,700 submissions, because each team one day can submit 3 submissions at most. And for task 2, more than 1,000 submissions. And yeah, the largest team make around 200 submissions. And there are more than 10,000 page views from about 100 countries, up to focus on this task. And here is some of the metrics. So NDCG, that is a normalized DCG. For ERR, which is a different metrics, you can read the paper if you're interested later. And generally speaking, ERR correlated with NDCG very well, but also my colleague Olivier, he believed that ERR correlated better than NDCG in terms of user metrics. And here is the correlation between the NDCG and ERR. But finally, the top winner, they are not necessarily correlated. But generally speaking, these two type of metrics, they are well correlated. And here is the submission over 90 days. As we see, like many different challenges or competitions at the beginning, there are some submissions, and in the last minute, right, there are quite a few, many submissions on the last 1 day or 2. And here is the distribution of the scores on the data set. So very important. So the best one in terms of, I think this is in terms of ERR. So we can ignore the number or the number of this number, but we can have a sense about it. So this one is 0.46 is the best one, and 0.43 is linear rank SVM, which is one of the most popular learning to rank algorithm based on SVM. And there is a huge gap between these two, and the major reason is the linear SVM is a linear model. So linear model is not successful in this task at all. And this, I believe, is ranked at the nice position, that is GBDT. So GBDT is ranked as the nice position, which surprised a lot of the researchers, because GBDT is a quite classical ranking algorithm. Actually, this is a regression-based ranking algorithm invented in 1999. And the #1 position is a team in Microsoft Research, and they dedicated to working on 1 month or 2. 7 people working on it, and the final model, they are ranked at the #1 position, and their model is based on ensemble learning. So some of you are familiar with ensemble learning. They use tens of different models, and combine together and have the best evaluation. But this kind of ensemble learning sometimes is not that practical, which means for example, they have 20 different models, which means the speed of this model will be 20 times slower. And ensemble learning is not that effective for real product. But the gap between the classical GPT and the winner position is approximately 0.5%. So which means compare different algorithms, compare different algorithms for this task on this data set, they are very, very similar. So in terms of the validation and testing, here is the 8 winning team. And we find that most of them, in terms of validation and testing, they are correlated and very, very limited overfitting. Only this one, I think the 4th position in task 2, there are some overfitting. On validation set, they keep increasing, but on testing data, the final result is not that good. And here is the result for each different team. For example, here is the winning team. They did a lot of offline research at the beginning, and in the last 1 month, right, they're starting to do this kind of to submit their validation result and hit the top position. Okay, and here is the winning team. In classical learning to rank problem, the position 1 is Microsoft Research. And actually, Chris Burgess, he wrote one of the first learning to rank papers in 2004, I believe. And the second position is I think they are individual researchers. They use really huge models, really complex models to find some good result. And the #3 is also Microsoft. The #4 is Yandex. #5 is Yandex. For track 2, Yandex is #1. Cornell University is #2. Yandex #3, etc. Okay, what is the conclusion for this challenge? So one conclusion is the best method, they are all tree-based method. So we can see it's a picture of forest, different trees, different trees. So all the winning teams are using trees. So none of the winning teams using like SVM, no matter it's linear SVM or kernel-based SVM, can get close to first top 10. And they also use different ensemble method, something like boosting, bagging, random forest, etc. And because there is no limit for the runtime complexity, which means some of their winning team, they have really, really huge model. The second position, the individual researcher, the model have more than 10,000 trees and more than 100,000 nodes. As we can imagine, this model they may get some evaluation metrics, but this kind of algorithm is not scalable at all. And the majority of the top competitors did regression and do not try specialized ranking, which means the list-wise ranking. And the top competitors are very, very close. And position 1 and position 2 on task 1, only 1%. I mean, the position 1 and position 8 or 9, that is GPT, only 0.5%. And there are some other conclusions for the whole learning to rank community. So I already mentioned in the year of 2008, 2007, 2009, there are many, many learning to rank papers in different algorithms because the data set is very small. So it is still possible for some of the researchers to do some data massage to find good result based on their algorithm. However, when this competition, this data set is released, and the benchmark data, right, you see the winning teams, they did a lot of effort, put a lot of efforts on it. And to some extent, the topic of learning to rank decreased dramatically because the researchers find, wow, the learning to rank algorithms is almost converged. So it is very difficult for a researcher to claim a new learning to rank algorithm to beat these kind of competitors. Otherwise, I mean, if a researcher, if a PhD student, you have a new algorithm and run on this data set and beat the winning team, the Microsoft or Yahoo or Google, they will chase you. But there are some other informative meaning for this competition. We find that, generally speaking, the classical learning to rank algorithm is mature enough. We call it mature. First is based on the competition, different algorithms, they are very, very similar. We have some other conclusion. I mean, nowadays we find different algorithms as long as they are converged, as long as the data set is big enough, right? The gap between different algorithms actually are very, very small. So one of the conclusions at that time, in the year of 2010 and 2011, so we believe learning to rank algorithm is quite mature. So after 2010 or 2011, the total amount of learning to rank papers are dramatically decreased. But what is the future direction for machine learning ranking? So originally we introduced in terms of loss function, we have point-wise, pair-wise, list-wise, but we still have some other challenges which is not solved by existing researchers. For example, how to handle the diversity from ranking. For example, if people search a query like Apple, whether he really want to search the result about Apple fruit or about Apple company, right? If a user want to search like Michael Jordan, so maybe for majority of people, just they want to search the basketball superstar. But, for machine learning expert, most of us will search for the machine learning superstar, which is a professor in UC Berkeley. And how to handle the transfer learning to rank, which is not well solved. Because for web search, right, there are so many different markets. So how to leverage how to transfer the knowledge from one market, like a US market, to a small market, and on web search, how to transfer knowledge from like web search to news search to Twitter search is also very challenging. And a big area called online learning for rank. So all the previous learning to rank is about train a model offline and test online. However, sometimes for some of the query, it is time sensitive, right? How to learn this kind of user click, user signals in real time and change the result almost in real time is a very challenging problem. We call the online learning. And sometimes there are some other terms called exploit, etc. So we write a paper about learning to rank, future direction in learning to rank in Journal of Machine Learning on 2011. And at that time, we believe that is the future direction. But until very recently, we find, wow, maybe there is another promising direction for learning to rank. That is about deep learning. So deep learning is very hot, very popular in the recent 1 or 2 years. Deep learning is just, based on the neural network. It has some breakthrough on some of their machine learning tasks. For example, on speech recognition, it's a very, very old classic machine learning task, and it's been 20 years, and the data set is huge, right? In the past, any new algorithm can only make very slightly improvement. But deep learning, I think sometime last year or the year before last year, they increased the boundary for like 20%. And for vision, computer vision, for image, each image can convert into a very high dimension feature vectors. For some of their vision tasks, like face recognition, I believe deep learning improve the state-of-the-art algorithm for more than 10%. So whether deep learning can improve the machine learning ranking problem is our question mark. So I know that many researchers on this community is trying to work on it. Because generally speaking, we believe machine learning ranking is a billion task, which means the top commercial search engine companies, they are heavily rely on ranking algorithms. Breakthrough of ranking algorithms can significantly improve user experience and the user satisfaction. So deep learning might be another very promising area for learning to rank topic. Okay, so that is the topic for section 1 and section 2. So shall we have a break right now? Okay, we can come back later. Questions? How to close it? First, let me try to close the mic. How to close? Okay, shall we start now? Okay, in the previous session, so I mainly talked about what is MLR and the state of the art of learning to rank algorithms on web application. The next two slides, in the next two sections, I will introduce more about some of the specific applications. Because as I mentioned, for classic learning to rank problems, web search is quite mature at that time. However, there's still some of the new challenges, new problems, specific problems on different applications. The number 3, section 3, I was talking about mainly about the dynamic web content, something related to freshness or recency. And the fourth one is mainly about the vertical search engine. Okay, so the first one is about recency ranking. That's trying to combine the relevance and freshness result together. So, for example, first question is why freshness is very important and very difficult. I think one of the questions you already mentioned at the beginning. For example, as we know that in the year of 2009, right, when Michael Jackson at one day suddenly dead, and we try different search engine, none of the search engine give a good result. So all of the search engine result are not good enough. The only reasonably result is based on some of the editorial-based method. And the same thing sounds like for some earthquake, right? In a news article, if an earthquake is breaking news queries or it happens suddenly, it is difficult for a search engine to return it on the top position. Why? Because as we discussed in the previous slides, all the machine learning ranking is based on editorial, is based on features. However, many of the many of the feature is time sensitive. For example, as I introduced, page rank is a very important feature. But for many new page, there's no page rank score. Click is it provides some very important features. But for a new news article or a new page, there's almost non-click, user click at all. So this kind of feature is very important. And to provide the editorial judgment for time-sensitive query is also very challenging. For example, like the Michael Jackson case, right? This query itself is time-sensitive. So the judgment is also time-sensitive. If on that day, the editor makes some judge, it is reasonable. But after 1 week, right, when it is not a news at all, user's judgment will become heavily, severely biased. So this kind of judgment is also difficult. So as a result, to provide very fresh content to the search engine user is a really challenging problem. We did some analysis. We believe based on all the traffic or all the queries in Yahoo search engine, approximately 5% of queries are breaking news queries, which means it is a really breaking news. And about a little bit less than 10% of queries are we call newsworthy queries. For example, there are some sounds like, for example, Beckham or Paris Hilton. They are celebrities, and they are irregularly make some news, attract a lot of people's eyeballs, attract a lot of news articles. So it is really difficult to say when this query will have news intent or not, but they irregularly have some news-related queries. So we call it newsworthy query. And generally, there are some overlap between breaking news and newsworthy. For example, Michael Jackson, we used to believe it is a newsworthy query, but when he died on that day, it became a breaking news query. So combine these two categories, around 10% of query are either news query or breaking news query. And there are some recurrent event queries, something like World Cup. It happened every 4 years, right? Every 4 years, there's a many query related to World Cup, like for some conference like CGR or KDD. It attracts many query at some patterns of the year. For example, before the deadline or around the notification. So this type of query, it is time related. If I want to search a query like CGR, I want to search the query of CGR this year instead of CGR last year or the year before. But maybe at the end of the year, it is still in 2013 when people search CGR, because the CGR 2013 is already passed. If you want to search, actually want to find the CGR in 2014 instead of 2013. So this kind of query we call recurrent event query is also very interesting and have some specific characteristics or some patterns. Okay, for recency ranking, we did some separate research, and we have 4 separate research. So the first part we call the recency ranking and data collection. That's mainly target for breaking news query and newsworthy query. And the second part is session-based click features for recency ranking. We're trying to bring some new features to handle both type of queries. And the third part is the recency ranking with Twitter data, also trying to handle the breaking news and newsworthy query. And fourth part is we use some feedback control adjustment method to trying to handle recurrent event query. And yeah, the overall challenge for time sensitiveness or freshness or recency for search engine, in terms of the feature challenge, first is precise get the timestamp for each document is very difficult. So when I starting to working on fresh recency ranking or freshness ranking problem, I had thought it is an easy problem, because I think for every document there are some timestamp, right? When this document is created, when this document is updated, we can leverage this kind of information to provide the best ranking. But then when I starting to working on it, I find it is very difficult, almost impossible, because the owner of the website, they can change it very easily. They can game it. They can cheat it. So as a result, we find many of the web page, the timestamp is not accurate at all. As a result, precise timestamp is not trustable at all. And there is very little click information for a fresh document, for a new document. There's very few anchor text for a fresh document. But this kind of anchor text, click information are most important features for learning to rank task. In terms of the data challenge, to crawl the very fresh document is very important, right? It's not trivial. And to label the data collection is also a challenge. We need real-time labeling, at least on the same day. We cannot ask editor to label breaking news queries after a week because people, mindset, have bias on it. And in terms of freshness, we need to provide new appropriate evaluation metrics. And in terms of the ranking algorithm challenge, traditional ranking would poor since the fresh document, they don't have in-link or click information. And in addition, we need to try to merge different source of result into one result. Okay, the first task, the first part is about recency ranking data collection. So this research is focused on data research part. And it is a paper published on Wisdom 2010. And for the label and collection, as we introduced before, for traditional data collection, that is for each query and URL, we ask editor to provide a label, PEG-FAB, perfect, excellent, fail, bad, good. But for recency label, we need to extend the bigram into the trigram. So for every query document and query time, we make a judgment. For example, if the time is very related, maybe the judgment is good. But if the time is not that fresh enough, the judgment will be different. So in terms of data collection, because we need almost real-time data collection, so we sample query every 1 day or 2 days to trying to reflect the true distribution of breaking news query, instead of just sample a lot of queries, a big chunk of queries, and ask editors to judge slowly. And data judgment also should be finished timely. Okay, so here is some of how we collect the training data. Still, we trying to break the grade into 2 dimensions. One is relevance grade, still perfect, excellent, good, fail, bad. And one is the recency grade, so fresh, which means that this document is very fresh to the query, reasonable fresh, or purely outdated. Then we're trying to combine these 2 dimensions into 1 dimension. For example, if a document, its relevance grade is excellent, but it is and its recency grade is fresh, so the final result is still we call the grade. But if the recency grade is reasonable, we are demoted for 1 grade, which means the final grade will downgrade from excellent to good. And if the recency grade is outdated, 2 grade demotion, which is downgraded from excellent to fail. And we did some analysis and find this kind of result is generally speaking reasonable. For those kind of judgment without any demotion, and we find the page age also judged by editors, is within around 2 to 3 days. If it's one graded demotion, we find many cases, their age is about 20 days or 40 days. If it's outdated demotion, right, we find many of the page have year or 1 year or several year age. And we collect a data set, for many different rounds. And every day we collect a small amount of data set, and for 3 months or 4 months, we collect multi-round of the data set to reflect the true distribution of breaking news queries. And in terms of the features, so in this work, we just provide some very, easy features. And one of our key findings, we find absolute timestamp doesn't make sense, which means we need to really leverage the relative age of the page compared with the query issuing time. And finally, we get tens of features. And we also leverage some of the timestamp feature, although it is not that accurate, and also leverage some of the link time features, bus features, etc. And however, also we collect many different round of data set separately, but each data set is small. And overall, the recency data set is still insufficient, which means if we only leverage this type of data set, maybe the recency is well covered, but the relevance is far worse than the original data set, which have millions of training data. So as a result, so we need to try to combine two different sets to provide an overall result which have both good relevance and good recency. So since recency training data itself, it will result to poor relevance, but good recency. But the regular training data have huge amount of data, have good relevance, but poor recency. So we have different method of combination. For example, we have some adaptation model. We have some overweighting model. Overweighting model is easy to understand. For example, we have some recency data, although it's small, right? We can put more data on it. And the regular data, we have more, we put less data on it. And then we use the pairwise ranking algorithm to combine them together. And in terms of the evaluation metrics, since we consider both the relevance and the recency, so in terms of evaluation, we also consider two different evaluation. One is the regular DCG without considering any demotion. That is just evaluate the original relevance. The second thing is, as I just mentioned, we have some demoted DCG, which is combine the relevance and the recency. So these two metrics together can give us a sense, what is our result.